In a previous video, I put together a PCB for a Lattice FPGA, an ICE40, and specifically this ICE40HX8K-CT256. And that's a 144-pin QFP that has quite a few I/O pins. And if I go over to the data sheet again for this real quick, I can look through the list of different packages in this ICE40 family. And again, I'm using an HX4K. And I had picked that one because it had the most I/O pins without me having to go to a BGA. And so this TQFP, I've had good luck soldering those in the past and working with those. So this was the most I/O in a format that I've worked with and had success with. Well, I thought it would be interesting to try to get a BGA working, and I am starting with this video maybe just to do some of the routing. I did a real quick community post a couple days ago and had just done the auto router, or used an auto router called free routing, just to kind of see if I could get it routed and what that looked like, and to get a feel for maybe what EasyEDA Pro looks like as I start to do a BGA, and also what free routing, how it behaves around a BGA type of chip or package. But in this video, I'm going to walk through, I do have it manually routed, and I thought I would walk through what I did to get to the point where I'm at on that, right or wrong. And so I'll put out the warning, I've never routed a BGA chip before, so this is my first BGA. And this is only within the software at this point, so I have not actually ordered this PCB, and the PCB is technically far from complete, but I'll show you that in a little bit. So I obviously haven't ordered it, I haven't tested it, so I don't know if this design will even work, but this is what I've got so far, and I'll get into it. But I'm going to use this 256 ball BGA, and they refer to it as a CA BGA, but it's a 14 millimeter squared with a 0.8 millimeter pitch between the balls. And that's obviously 256 balls or pins on that BGA. And they're saying that that should give me a usable 206 I/O. And that's what entices me with this BGA package is all that I/O. There's so much I could do with that. Especially as I'm working on some of these retro builds, 386, 46, whatever it might be, I really could consolidate a lot of just glue logic and other timing type of stuff into one of these and really cover the entire system. Now, as I get into this, there's probably a few things I want to look at. First of all, I have to pay attention to the power filtering on this. And this is really just a document on hardware checklist, but it talks about all the capacitors that I should have on VCC and VCC I/O, etc. So I had to make sure I was working through that okay. And then also there's some recommendations, and they actually have recommendations for this specific package. This CT256 is at the end of the part number. But here's an example of how Lattice suggests you could do this with a 6-layer. Now, to complicate things, though, I've got to take that and put it side by side with what can I actually do with JLC PCB, which is who I want to use at least, or who I've been using for my manufacturing. And so I've got a blog post, and it's called My Personal PCB Checklist, and I've just been using it to capture what I'm using for different settings and how I'm getting into some of the routing and PCB design. But I added some content in here that is probably more for my benefit than anything, just so I remember all of these settings. But if you're curious on what settings I've used as I go through this, I think I've captured everything here, or I'll continue to update this at least as I go. So I list out the part I'm using, again, 256 balls. The package is called a CA BGA, 16 millimeter squared, 0.8 pitch, and 206 I/O. And then I have links to a few really handy documents. And so I'm going with a 6-layer setup. And with that 6-layer setup, what you see here is what I'm looking at for the sample spec off to the right. So to the right here, I can see that they're saying, well, okay, you can probably use 6 layers, do a solder pad of 0.2 millimeter, work my way down to a drill of 0.1270 and pad size for the via. So it's a via size drill, via size for the pad, and they're showing 0.2540, a trace width and a trace spacing. And if I go over and take a look at what can JLC PCB do, I'll find that they can't necessarily get all of the values that I'd like to get to. For example, when I get down into this, one of the things that I found challenging is, for example, this pad to track. And so there's a 0.2 millimeter minimum, and I believe that pad to track, there's also a, let's see, I think that is going to also be the fill. And let me come back up here, and I'm looking for something here, pad to copper pour, and I will do a search and see if I can find this in here. But JLC PCB has a minimum distance between a pad and a copper pour of 0.2 millimeter. So that was also a challenge that I ran into. And I'll get in and maybe show a little bit of this in the tool in a minute. But anyways, I was going through these and trying to just figure out what can JLC PCB do. What do I probably need to do if I'm going to be using JLC PCB? And so I've been trying to capture some of that here, and this is incomplete, but they're maybe saying, well, a 0.2 millimeter for the BGA solder pad size is what their sample is off to the right here. If I go to JLC PCB, the minimum they can do is 0.25, but if I want to do via in pad, which I do, they're saying that you really should have a 0.4 millimeter pad. And I am using a component that is this actual FPGA that is from JLC PCB's system library. So it's one that I have fairly high confidence it's probably put together correctly. And it has a ball size, or this BGA solder pad size, I should say, of 0.36 millimeter. And that's what I'm going to go with, is I'm just going to use that as is. I'm not going to try to modify the existing component. So I'm going to go with a 0.36. So that's quite a bit larger pad size than what the Lattice example is going with. But if I want to do via in pad, JLC PCB is suggesting I should be at a 0.4 is recommended. 0.36 I think I'll be okay, and I guess I'll find out if I get to the point of actually ordering this, if they kick it back with any type of an issue. They get into the via size for the drill and also the pad, and over here I've got what are the minimums according to JLC PCB. So this via size for drill, the minimum I can go down to, I believe, is 0.20. And maybe I can go a little bit smaller than that, and I'll be able to actually come over here and let's just go look up via, see if I can find drill hole sizes. And it looks like for the multi-layer, the drill holes I can get down to 0.15. Minimum via hole size on multi-layer. So 0.15 is the smallest via hole size I can use, and a diameter of 0.25. And so when I'm over here and I'm looking at this, I've got 0.2 and 0.3 is what I'm going to use, even though here it does look like I can go a little bit smaller than that. But these values were recommended in a different document that I've referenced in here, which is there's a JLC PCB BGA document that they put together. And reading through this, they have some recommendation here also where the drill, they're saying minimum should be 0.2. The diameter should be 0.3. So they've given some stuff here that I also have to take into consideration, but I've been trying to reconcile all of that into what you see highlighted in this bold orange is what I've actually gone with, at least for the design rules. Now I will note that when I get into this, I set the design rules to say allow down 2.09 for the trace width and spacing, but I actually used 0.1 as I get into it, and I can double check that here and when I pull it up in a little bit. But that's the type of stuff I'm just having to verify is what does JLC PCB say that they can do and recommend for FPGAs. They have another set of documentation for what they say their manufacturing capabilities are. And then I am trying to take all of that and make this specific package actually workable. So maybe with that, what I'll do is I'll jump over. Here is the project that I'm working on. And if I take a look at this, really there's not a whole lot here yet, but the hardest part is done, I believe. So if I go to 3D, it's going to look quite boring. You're going to see there is my BGA, that Lattice FPGA, the 256 ball. And I've got a power connector, and then I just simply got some regulators to give me my voltages. And so I've got 5 volt coming in. I need a 1.2 volt to run the FPGA. I need a 3.3 volt for things like I/O and SPI, and then there's also a 2.5 volt that's used to do onboard one-time programming if I decide to ever use that feature. But what I did is I just did manual routing to try to get this fan out to work. And then on the bottom side, I've placed all of the capacitors. And I've placed those, kind of as close as I can. I suppose I could technically get closer as I look at this, but I wanted to give myself some space. I could not put them down underneath, and maybe someone here can recommend something there, but JLC PCB does not support vias that don't go all the way through. And if I go back, let me pull something up real quick here. If you look up JLC PCB via, I think they've got a little article here about, that's not the one I want. And so they have this article, and they talk about a few types of vias. There's through hole, blind, and buried. They don't support blind or buried. So all of the vias I have to go all the way through the PCB. And so what that means is that anytime I'm going to do a via in pad, it's going to come all the way through, which means I really can't set a capacitor on top of that. But what I did do for my capacitors is I put a larger, basically via in pad on those just to really minimize how many traces I'm running for these capacitors. And I have inner plane that is supporting getting all of that power distributed in a decent way. And so let me go over to the design now that you kind of see what I have here and just walk through, I guess, what all I had to do to get that to work. And I might flip back. I've put in some notes in this here, this page, and I just listed some general steps. And so I went with a 6 layer. So if I go look at this and I can look at my copper and see what copper I have, I can look at the stack up as a 6 layer. And basically I'm doing a signal, and another signal, even though this one is really all power, but I am going to go ahead and basically do copper fills with my different power planes or mini planes or planelets, whatever the appropriate term is there. Planelet, I think, is what I'm seeing people say. Then I do have a true plane zone that is for my ground, and then I have a signal and a signal. Now in the Lattice sample, they did a signal. Well, they pretty much did the same thing. They did 2 signals, they did a power plane basically broken up into the different rails, the different 3.3, 1.2, whatever it might be, ground, and then a signal. So I'm following something I think that's pretty close to what they're doing there. And so then if I go into this, on the ground, if I take a look at the ground plane for a second, let me go back to this copper region. Okay. I've got these hidden, so let me unhide those. So if I go to ground, there is basically just one large plane that is tied to the ground net. If I go to the, let's say power, you're going to see that I have a chunk here that is a 2.5 volt. So the net is 2V5, and that's going to go underneath and get that to the right pin that I need for the 2.5 volt. I have one here that is the 1.2 volt, and that's going to basically make sure I have this, this copper fill that covers all of the 1.2 pins on the FPGA. I have a 5 volt up here, and so that's really coming in 5 volt, and then that basically has to distribute it over to these voltage regulators. So I've got one here that's going to go to my, this is my 5 volt in, then I got my 1.2 here. I also get my 5 volt all the way over here, and I pull out of that. This is my 3.3. I know that's really hard to see, but I've got my 1.2 and my 3.3. They're getting a nice clean 5 volts to them. And then over here, I am also doing this 2.5, which I don't think I'm ever going to use. But then just to kind of be safe, I did run some pretty thick traces over to that if I ever do decide to use that. But that I don't think is going to get used much. But what you'll see here then is that when I come underneath my FPGA, I'm either going to have, this coming in as my 3.3, or this coming in as, that's my 1.2, there's my 2.5, and there's my 3.3 covering the other pins that are 3.3 volt. I'm sure I could spend a lot more time on this and do a better job, but this seems like it gets the pins for power and ground set up so that I don't need to run any traces. I'm just going to drop a via in pad right to the portion of this layer to get my power. And so that is this power layer, which I'm going to just hide for now, and I'm going to hide my ground plane also. And then I'll go back up to the top layer for a second. And let's see. Let me zoom into this for a second. Again, 5 volt coming in, getting to my 3 regulators, and then coming out 1.2, 3.3, and 2.5. Now, obviously, at some point, I need more than just the FPGA, so then I will come in here and put in headers and other stuff if this is just going to be a dev test type of board to see if I can even make it work. So I made a pretty large PCB here, and if I look at the size of this just for a second, you can see that the width is 195 and the height is 95. Now, going from maybe I can squeeze this down later to fit within 100 by 100. That will lower the cost of the board. But for now, I'm going to give myself a bunch of space, and then if I need to shrink it down later, I can do that. We'll see. I just have a lot of headers. If I actually want, I don't know if on a dev board I need it, but if I want to actually expose all of those I/O pins, that's 200 and some pins, and even with a 1.27 millimeter pitch for those, that's going to be a lot. If I do zoom in here, let me take a look at the bottom layer first. And so I'm going to hide all of these and just bring up, see the bottom side. So I'll get rid of most everything here and just focus on the bottom for a second. And so you can see I have all these capacitors, and essentially what I did, and let me bring this all back up for a second. You'll see that for each capacitor, Now these are small capacitors. These are 603s. So I'm using a 603 for a size, and I am following the recommendations. So I have two different size capacitors that I'm mostly using or entirely using. And that would get me into these here, the 4.7 microfarad and the 0.1 microfarad. But that's what you're going to see here. And then I've placed in a basically a pad, via in pad here that will directly connect me like here to my 3 volt or directly to my ground. So there's no traces coming out of this, and I did make these larger, so these are pretty good size. So 0.254 for the drill and 0.508 for the outside diameter. I think that's fine to do that. If anybody has any thoughts on that, let me know. But I know I've been watching a bunch of videos, and it seems like that is, I'm sure there's pros and cons, but it seems like that's acceptable to do that. So then I've got all these caps laid out, and again, I really couldn't effectively put it underneath. So I kind of just tried to space them out. Seems like a lot of capacitors, but the documentation is saying for every pin I should have, every power pin I should have a pair. And so for every VCC I need these two, but I could maybe, I don't know, it does say per pin, per pin, per pin. So that's what I did. So I've got this pair of capacitors for every VCC pin. I've got this pair for every VCC IO pin. That's what I've kind of laid out here the best I can. Again, maybe isn't ideal. I don't know. This is my first run at this. So if you've got thoughts on capacitor layout, do let me know. And I'm sure if I go back to the reference design, I could look at maybe how it was done. Now, if I do maybe jump back for 1 second and I look at this and I look at their layout recommendations, they might be making some assumptions on capabilities that I'm not going to have with JLC PCB. And I also noticed that they're not doing via in pad. They're actually doing a fan out. Maybe this is more of a traditional BGA fan out approach, but that's how they're approaching it. And I decided to go with the via in pad. And the reason I did that is, first of all, JLC PCB, that was a recommendation that they have, is to leverage that. So if I go back, they have a BGA guidelines, and where possible use via in pad, and so they give some detail on that, but that's what I'm doing. If I get maybe now to, maybe I'll jump up to the top layer, and maybe I can hide everything but the top. That just kind of shows you the fan out that I did here on this top layer. So remember, I've got 4 signals, 4 signal layers here that I'm using for actual routing. So this is what I did for the top layer. If I go down a layer, let's see, that'd be my signal 1, and I'll hide the top. So let's see, hide the top, go to signal 1. You can kind of see what that looks like. If I then go down to the next signal layer, that would be signal 2, and it looks like that. And then, of course, I'd get to the bottom of the board, which is going to look like that. So it should be that between all of those, I've got every pin covered. And maybe I'll take out the ground and power planes for a second, but that's what it looks like. These pins in the middle that don't look like they have anything hooked up to them, that's just because they're power pins and they're going straight into the power layer and connecting to the corresponding 3 volt ground, whatever it might be. Now, maybe some things that I learned as I went through this. First of all, if I do come in and look at these, let me just pick my top layer for a second, and I'll pick one of these. You can see that my line width is 0.099. So basically 0.1, I think, is what I set it up for. So when I was coming in here and I start drawing a wire, I just set up a shortcut to go to 0.1, and it looks like it's actually plugging it in as that 0.099. So that's what I'll use there. As I get further out, I'll switch to something thicker, or wider, but at least for what I've got so far here, this is what I'm coming out is a 0.1. As I got into this, there were definitely limitations, and this fits, but I definitely cannot fit 2 traces in here. Part of that is if I go into the design rules, there is, I'll just leave this up for a second so you can look at some of the design rules. So first of all, this is spacing. So between tracks, I can go down all the way down to 0.09, so that's fine. But then my track to pad, track to via, you can see the values here of 0.152. And then I'd have to go back and double check with the documentation from JLC PCB and see if that is supported. When you first come in here, you can choose a configuration, and I started with the JLC PCB capability multi-layers, and the ones that I did modify, I try to keep it within spec of what was stated on their website. So I'll find out when I actually get this sent over to JLC PCB if there's any issues with it. Let's see, other things though, I can look at my track physics. So I've got the spacing, and then I've got the actual track configuration itself, and I got that set to 0.09, but I was really using that 0.1 as I was doing all of my track drawing. I've got my via size, and here I'm doing a 0.2 inner or the drill, and a 0.3 for my overall or outer diameter. And then I had to come down and look at the copper regions and shrink this down. This is the minimum I can go with JLC PCB is 0.2. So what I'm finding is that once I put my via in a pad, and I've got 2 of those side by side, I can only fit 1 trace in between. So that, I think, is just basically comes down to a limitation of JLC PCB at this point, which was okay. I with that thought I might have to go to 8 layers, but it ended up I didn't have too much of a problem getting this routed out as you see it here. There's a lot of stuff I know I'm probably not taking into account. I know some of these signals should be paired up. I know there's probably trying to keep all of the signals the same distance or close to the same length, I guess, of signals. I'm really not worrying about that right now. And I have to get all the rest of this PCB put together where I'll tie off of. So, for example, I might come into one of these. I'll make sure I'm on my top layer. I'll draw a wire. I'll change the wire size. Maybe I go to 0.254, and then I'll just draw out from there using that size wire. So a lot of these I'll have to further separate out, because you might find that I've got multiple layers kind of stacked on top of the same locations here. But that's easy to do from the stage where I'm at right now. Maybe one thing I didn't do is on my top and bottom layers, I didn't put in any fill. And I will do that before I'm done. So I will do a fill on the top and the bottom. And I don't know yet if one of those will be ground and another one will be 3 volt or something like that. We'll see when I get there. Something else I found is that when I got to the actual power here, and I was filling these in, it's like here, I'll pick this one. You can kind of see it's all of this. This is my 3 volt, or if I pick this one, that's my 1.2 volt, and that should cover all the 1.2 volt pins. So, I drew this in a way that any 1.2 pins should have something coming right up to it, and you can see that accordingly. And maybe I could pull that down a little bit further, but this is, I think, sufficient where I've got it. So these are completely surrounded. This, I got something coming up to it. I could, again, pull that in further. Possibly that might be something I could do later. But I found that when I got into this, there is a setting and it says optimization, and it defaults to yes. And when I do default it to yes, it doesn't actually allow the fill to get in past all of these. And so it breaks it all up. It really doesn't fill it in like it should. So I had to set this optimization to no. But then at that point, I've got this fill and I've got these contiguous spaces. And that all seems to be working out okay. If I go back to my notes here real quick, there's a fan out option, which is kind of neat in EasyEDA Pro here. You can pick the IC and then you can go in and say that you'd like to do a fan out. And if you pick via and pad, it'll basically run through all of the pads and put the vias inside of them for you. And then from there, you can easily take out maybe the outer 2 rows. And that's what I did. So if I go back maybe to my layers and I'll go to my top layer, you'll see that I have via and pad in these, but not these up here. And basically I just picked the IC. I said, do that route fan out. I chose via and pad. Everyone then came up. And then there's a filter, and I can filter it and say, just let me modify vias. And I can quickly drag and highlight an area, and just the vias get highlighted, and I would hit delete. And so then that ended up with a real quick way of having all of these pads there, vias on all of the inner ones. And that's where I started. And then I just kind of added in the 3/3s and the grounds and all that stuff as I built this out. But that was pretty quick to do. Maybe a note, the default pad size again is 0.36 on the component I use. So this component that I brought in, let me go back to the schematic, looks like this. And this again is from the system library. So basically EasyEDA and JLC PCB, there was something they're supplying, not community supplied. But I went in and looked at the design of it and saw that basically they're using a 0.36 millimeter for the pads. I think JLC PCB would technically prefer 4.4 if I'm going to do via in pad, but I think I'll be okay with this. Then I did all my routing and ended up with what you're seeing. So I'll go back over here. I think that's about it. So if I did a DRC check, that comes up clean. So I've got no DRC errors. I think, unless I've missed something somewhere, this should all be manufacturable by JLC PCB. And then, of course, is it something that I can assemble would be the next question. I do have an IR oven, I have a hot plate, I have a hot air station. So those are the tools at my disposal to try to work on this BGA. I don't have any BGA specific equipment. So I think if I order this, what I would do is probably order it with a stencil and try it on my oven and see if I could get this properly soldered. So that's a concern I have. I don't know if I'll be successful there or not, but I'll have to try it. I do also know that this is an expensive board. And so if I go to order it, and yeah, DRC should come up clean. But then it comes up and it says, okay, you want to go ahead and order this, and it's uploading my files. Their system checks out the Gerber files and then says here's a price, and that price is going to look high, and it's still not high enough because I have to come down here. It is selecting the 6-layer high precision PCB. I'm using a 6-layer. It shows me my dimensions, but one of the settings I have to change, and it doesn't detect it automatically, and so it's a minimum via hole size, and I'm using this 0.2 as my drill and 0.3. And as soon as I check that, you can see they add on a bunch of fees. So the engineering fee is pretty high here. the minimum via hole size, since I dropped from a 0.3, 0.4 down to a 0.2, 0.3, so that's the inner outer. They added on a $18 fee to do that, and because some of these are so small, they have this mandatory 4-wire Kelvin test that they add on. So you can see that added basically $34, $35. The board itself is only $11, but this engineering fee is quite expensive. And then it would probably have another few bucks for shipping on top of that, $112. And actually so probably looking at about $115 unless I go with the fast shipping, which is what this estimate is for. So they're expensive, and so I'm a little hesitant to order this until I get to the point where I've maybe tested this previous board and know that I can actually program it and work with it in an okay way. Then I can adjust this design, maybe to take into account some of these considerations, add some memory, some static RAM, add a bunch of headers, double the headers that this board here has. And then that could be the stage at which I would order up this PCB here. But I think that's about it. So I am trying to just kind of take notes on this. So if any of you if you're experienced and done a BGA like this with JLC PCB and you have other tips or tricks or gotchas, things that I'm going to run into problems with, let me know, and I can definitely add them here to the notes so others can take a look at that. And if I get to the point where I order this and get it and test it, if it's something that's workable, of course, then I could also post some of these design files if anybody else would find them helpful. I'm not expecting that this is an A grade for my initial work on an FPGA, but hopefully it's something workable. And it's not using an auto router, so there was no auto routing on this at all. This was all done entirely by hand. And I found it wasn't so bad once I got used to just working with EasyEDA Pro, because this is fairly new to me also. But that all seemed to be okay as I went through that. If you have any feedback on this, something that you'd recommend I take a look at, please let me know. If you've got questions, drop me a note, and I'll do my best to try to answer. So more to come on this specific FPGA down the road. I backed up with projects. I have a whole bunch of stuff sitting on my workbench. I've got a new power distribution module that I put together that allows me to use these new connectors here. This 2-pin Molex connector here. That's kind of my standard power connector moving forward. So I did put together a little board on that goes into a little enclosure with the connectors that take in banana plugs and kick these out. So I've got to get that. I put one together, but I'm going to put another one together. I need to get that done. I have a couple of the different MCU boards I was working on before that finally came in. And then I have en route this previous FPGA board. This one here is en route right now. So that's a whole lot of stuff for me to work through. That's going to take some time. And then if I get that far, that's when I would come back to this project, update this based on what I learned on this board, and then try to get this one ordered up. Then maybe I have to think about back on my 486 build, which I would have to go over to EasyEDA standard. That's where I have that project at. I'm not going to jump there right now, but I've been using these PSOCs, and I did a bunch of work to see if I could just consolidate down to one larger PSOC, and that was my plan. Maybe still is my plan, but this FPGA stuff is really intriguing, and with all these I/O pins, it's kind of a pain, I would say, to get this on a board, and maybe the BGA is going to be too much of a challenge for me on the assembly side. But if I can manage that, that really opens up some pretty cool opportunities on my 486 build that I've been working on, which has been sitting for a little while now. I haven't done anything with that as I've gotten into some of these MCUs and FPGA and such. But I will eventually get back to that. It may be a couple of months yet because I'm enjoying working on some of this stuff. This FPGA stuff's pretty cool. These MCUs I know are old, but I'm finding those to be pretty fun as I go through this here. And I've got a whole list of, I've worked through one. I've got two others that are ready to go. I think it was those two. And then I have a whole list of others that I could be working with. And then, of course, this is an FPGA that I'm working with now, not an MCU. But maybe I'll keep working through some of these others just for the experience. Okay, that's it. I'm going to stop there. Thanks, everybody. Appreciate the likes and subscriptions and comments and feedback, suggestions, all of that. So thank you all very much.